In this lesson, we are going to review the contents from Midterm Numbers 2 and 3, which is chapters 7 through 12 of your textbook. So chapter 7 dealt with probability, and here are some of the basic probability examples. So a person has agreed to participate in an extrasensory perception experiment. He is asked to randomly pick two numbers between 1 and 6. The second number must be different than the first. So let's let H be the event that the first number picked is a 3, and K be the event that the second number picked exceeds a 4. Okay, so first, probability of H. So what's the probability the first number he picks is a 3? Well, there is one number that's a 3 out of 6 total numbers. So P of H is 1/6, which as a decimal is 0.16 repeating, but you can just leave those as fractions. Probability of K given H. For these, I always find it helpful to translate them into words first. Probability that the second number is bigger than 4 given the first number is a 3. Okay, so how many numbers are bigger than 4? There are 2, and because the first number chosen is a 3, and the second number must be different than a first, there's only 5 numbers to pick from. So in that case, the probability is 2/5, or 0.4. So I think it does help a lot to write down what that means there. And this word, you have to know what exceeds mean, but exceeds means greater than. So now let's find the probability that K and H both occur. So the event that the first number picked is a 3, and that the second number is bigger than 4. If these events were independent, then you could say P of K and H is P of K times P of H. But we don't actually know that that's true. So we are going to say this is equal to P of K times P of H given K. And that's actually not that helpful because in parts A and B we had the probability of H and probability of K given H. But you also know that this is equal to P of H times P of K given H. For those of you that need to look this up, this is Rule 3 on page 239 of your textbook in section 7.4. But if you think about this intuitively, think about this. The first number you pick is a 3. That has probability of happening 1 in 6. Then the chances that the second number you pick is a 4, or is bigger than 4, we just found that knowing the first number is 3, that's 2 in 5. So this ends up being 2 over 30, which reduces to 1/15. Find the probability that both numbers picked are less than 3. So what's the probability that the first number less than 3 and second number less than 3? Okay, well, the numbers that are less than 3 are 1 and 2. So the chances that that first number is less than 3, there are 2 out of 6. Now, for the second number to be less than 3, you've chosen one of those 2, leaving only one left out of 5 numbers to choose from. So that ends up being 2 out of 30 again, or 1/15 as well. And if you think about it this way, you can avoid the whole rules that are Rule 3b. This is more like the intuitive way. First number being less than 3, second number being less than 3 as well. Okay, a survey of college students found that 56% live in a campus residence, 62% use a meal plan, and 42% do both. Let R denote the event that a randomly selected college student lives in a residence hall, and let M denote the event that a randomly selected college student uses a campus meal plan. What's the probability that a randomly selected college student lives in a campus residence hall or has a campus meal plan? So what you want is probability of R or M. And when I graded your second midterms, this is a common mistake. People said P of R plus P of M. And let's discuss why that definitely has to be wrong. Well, the probability you live in a residence hall is 56% or 0.56. The probability you use a meal plan is 0.62. And if you add those two things up, you get some kind of quantity that's bigger than 1. So that's obviously incorrect. So the rule states you have to also take away the chances that you have a residence hall and a meal plan. Think about this as a Venn diagram. Here's people in residence halls. Here's people in meal plans. P of R figures out that group. P of M figures out this group. And what you've done with this stuff in the middle is that you've counted it twice. And that's why you have to take this away. And we're told that 42% do both. So we take away 0.42, and then we get a more reasonable answer of 0.76. Okay, given that a randomly selected college student has a meal plan, what's the probability that they live in a campus residence hall? So the given is the thing that goes second. Probability in residence hall given meal plan. And one of your probability rules states that this is equal to P of R and M divided by P of M. And the basic idea here is this, is if you know somebody has a meal plan, that's going to increase the chances that they live in a residence hall. Okay, well, P of R and M is 0.42 divided by P of M, which is 0.62. Comes out to be 0.677. And note that this is higher than P of R, which is 0.56. So knowing somebody has a meal plan increases the chance that they live in a residence hall. Are the events of R and M independent? Explain your answer. I think the easiest way to check independence is to check, does P of R and M equal P of R times P of M? That's the best way. You know P of R and M is 0.42, and you know that P of R is 0.56, and P of M is 0.62. So is 0.42 equal to that product? Well, that product is 0.3472, so no, those are not equal. So no, as P of R and M is not equal to P of R times P of M, these events are dependent. You also can think that, well, knowing somebody has a meal plan influences the chances that they're going to be in residence hall. But I'd prefer that you check this way because the intuition often fails. All right. Suppose that only 2% of individuals undergoing a particular medical test have the disease the test is intending to identify. If an individual has the disease, the chances the test will find it correctly is 0.9, and if an individual does not have the disease, the probability the test falsely gives a positive result is 0.05. We're going to make a hypothetical 100,000 table for the situation, and we can also make a tree for those of you that like that better. So we have the positive test, negative test, people that have the disease, people that don't have the disease. Okay, so if we have 100,000 people total, so the first thing we know is that 2% of people actually have the disease. So here, 100,000 times 0.02 gives us 2,000 people who actually have the disease, which tells us that 98,000 do not. That's your first step. Next, if an individual has the disease, the chances the test will correctly identify the presence of the disease is 0.9. Okay, so that means that if you have the disease, test positive with 90% accuracy. So 2,000 times 0.9. Of those 2,000 people, 1,800 will test positive, leaving 200 who are actually sick but still test negative. If an individual does not have the disease, the probability the test falsely gives a positive result is 0.05. So no disease, positive test. 98,000 times 0.05, so 4,900, leaving 93,100 people in that category. And then adding up my positive column and negative column, I end up with 6,700 and 93,300. If you like the tree better, you can do that as long as you do it correctly. So step 1, we have disease and no disease. So the chances you have the disease, 0.02, no disease, 0.98. Now, if you have disease, the chances that you test positive are 0.9. Therefore, chances you test negative, 0.1. No disease, the chance you test positive is 0.05. Test negative, 0.95. And multiplying across those probabilities, you get this is 18 decimal over 1, 2, 3 spots, so 0.018. This one, 2 decimal over 3 spots, 1, 2, 0.002. .98 times 0.05 comes out to be 0.049, and 0.98 times 0.95 gives us 0.931. And if you add all these numbers up, you should get 1. Which we do. Okay. So either the table or the tree, I'll let you choose which one you like better, but if you do the tree, you have to find those numbers. Now, if the test result for an individual is positive, what's the probability this person has the disease? So probability of disease given positive test. And this is where the table really is better. So of the people who have a positive test, how many have the disease? Well, there are 1,800 who have the disease out of 6,700 total positive tests, which is a probability of 0.269. If you use the tree, you've got to do it like this. Probability of disease and positive test divided by probability of positive test. Okay. Okay, so disease and positive test in your tree, hold on a sec, would be 0.018. And then there are two ways to get this positive test. You could be positive and have the disease, or you could be positive and no disease. Okay, so look back at your tree. Positive and disease is 0.018 plus positive and no disease is 0.049. When you put that in a calculator, make sure you put parentheses here. So 0.018 divided by 0.018 plus 0.049 gives us the exact same thing, 0.269. So I do understand that for lots of you the tree is more intuitive, but this calculation, which is really the crux of why we do that, is less intuitive with the tree than with the table. But they're the same, so whichever you like better. Of the following random variables, classify each of these as discrete or continuous. So remember that discrete will have categories, and it'll be in order. So toss a coin 3 times, record the number of tails. Well, you can't have half numbers of tails, so this is a discrete random variable. And the number of tails, just, for fun, the options, the number of tails you could have could be 0, 1, 2, or 3. Weigh a coin, record the weight. That's a continuous random variable. So suppose that I have a new treatment for a disease, and if I apply this treatment to a randomly selected participant, there's an 80% chance, or 0.8 probability, that they recover. Suppose I apply this treatment to 4 patients, and let X be the number of patients who recover. Find the probability that X equals 3, and describe what it means. Well, X is a binomial random variable with success probability 0.8 and n equals 4. So remember, the probability that X equals a specific k value is n factorial over k factorial n minus k factorial p to the k 1 minus p to the n minus k. So this is 4 factorial, and we care specifically about x equals 3. So 4 factorial over 3 factorial, 4 minus 3 factorial, 0.8 to the third, 1 minus 0.8 to the 4 minus 3. What you can think is you've got 4 patients, and you either could have recover, 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 no. And you could have had recover, recover, no, recover. This number out in front is calculating the number of ways you can arrange those r's and n's. And this 0.8 to the third is taking account for 1, 2, 3 recovers. And this, which is 0.2, is the one not recover. Okay, so remember that 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 1 factorial is just 1. 0.8 to the third, and then 0.2 to the first. Well, look, this 3, 2, 1 cancels with that 3, 2, 1, giving us 4 times 0.8 cubed times 0.2, which you can then calculate to 0.4096. And then what does it mean? So this is the probability that exactly 3 out of the 4 patients recover. So next, Consider the probability distribution function for year at school for undergraduates enrolled in introductory statistics courses at a certain university. What's the probability that a randomly selected student from this population has been in school for at least 3 years? So at least means 3 or more. So probability that x is bigger than or equal to 3. Well, that's equal to 0.24 plus 0.08, which comes out to be 0.32. So 32% chance that the person taking statistics has been in school for 3 or more years. Find the expected value for the number of years a student from this population has been in school and describe what this value means. Well, remember that expected value is given by the sum of the probabilities times the x's. So in this case, our first probability is 0.08 times 1 plus 0.60 times 2 plus 0.24 times 3 and plus 0.08 times 4, which comes out to be 2.32. Okay, and what this means is that the average student taking introductory statistics is 2.32 years into their school career, or into their schooling. So that just tells you what the average year in school a person is when they take introductory stats. And notice that, somebody can't actually be 2.32 years into school. So on average, they're a little bit more than 2 years into school, is what that means. So find the standard deviation of the number of years. Well, first we'll find the variance, which is given by the sum of the x's minus the mean squared multiplied by the probabilities, and then we'll take the square root of that. So we have 1 minus 2.32 squared with probability 0.08 plus 2 minus 2.32 squared, probability 0.6 plus 3 minus 2.32 squared, probability 0.24, and then finally 4 minus 2.32 squared, probability 0.08. And that comes out to be, try to punch in your calculator in one go instead of a little piece at a time, 1 minus 2.32 squared times 0.08 plus 2 minus 2.32 squared times 0.6 plus 3 minus 2.32 squared times 0.24 plus 4 minus 2.32 squared times 0.08. Comes out to be 0.5376, and that's our variance. Sigma, which is the standard deviation, is the square root of this number. So second square root, second answer, gives us about 0.7332. Another important skill that you remember is how to use a standard normal variable to compute probabilities. So suppose that newborn birth weights in the U.S. are normally distributed with a mean of 3,420 grams and a standard deviation of 500 grams. So the first thing you should do here is standardize. So remember that you standardize by taking your x value minus your mean divided by your standard deviation. And here we care to standardize 4,000. So 4,000 minus 3,420 divided by 500 should give you 1.16. So what are the chances that a randomly selected baby is going to weigh less than 4,000 grams is the same as asking the question, what's the chances some normal variable, standard normal, is less than or equal to 1.16. What we computed there is that 4,000 is 1.16 standard deviations away from that mean. And looking at your table, you get that this is 0.8770. Okay. Next, what's the chances that a baby is bigger than 3,000 grams? Well, first find that z value. So 3,000 minus 3,420 over 500, which comes out to be negative 0.84. So this is the probability that a z is bigger than or equal to negative 0.84. Okay, so I want this probability. Well, that's the same as 1 minus probability that z is less than or equal to negative 0.84. Well, that's 1 minus 0.2005, or 0.7995. And remember that your tables, by default, only go down, so you have to do this little complementary action here. Okay, this is asking what's the chances a baby's weight is in between 3,000 grams and 4,000 grams. Well, we already did the work. That's probably the z values in between negative 0.84 and 1.16. If you draw a picture, you'll make fewer mistakes. So there's 1.16, there's negative 0.84. So obviously you want to find that number, which is probability that z is less than or equal to 1.16, and you want to take away that bit. And then you'll have this area in the middle. And the purple thing you actually found in part A to be 0.8770. In part B, the probability that z was less than negative 0.84, you found to be 0.2005. The tricky thing there, some of you blindly just use the answer from B instead of thinking, oh, I need that probability, which is not my answer, but the thing I used to get my answer. So this comes out to be 0.6765. And a lot of students are freaked out because this inequality seems to change directions there, and they don't understand why, but the why really is this picture. So if you think about that picture, you'll understand why that has to happen. To find this middle area, you must take away that area, and that area is z less than that number. That's the reason. So one of the most intuitive rules is the complement rule, but it turns out it's one of the trickiest ones to apply, and this is an example of that. Suppose that the probability of winning a particular casino game is 0.1 and is independent from one game to the next. If someone plays the game 10 times, what's the probability they're going to win at least once? So what are the chances you win at least once? And the tricky thing about that is you could win once, you could win twice, you could win 3 times, or you could win every single time. So how do you account for that? Well, that's the opposite of never winning. Okay, and how do you never win? Well, chances you never win once are 0.9, all 10 times 0.9 to the 10th. And this comes out to be 0.651. So this is never win 10 times in a row. Here's one thing that's wrong. 0.1 to the 10th. What this actually is winning all 10. That's not what the question asked. The question asks, what's the chances you're going to win at least once? So you could win all 10, you could win 9 out of 10, 8 out of 10, 7 out of 10. So you could compute those each individually, but it's really complicated, and so this complement rule is the best way to go. And some hint that that's what's going to happen is you'll see the words at least once. In computing a confidence interval for population proportion, will a larger confidence level result in a wider or narrower interval? Give a short explanation for your answer. Okay, so say we have a 90% confidence level versus a 99% level. Well, the higher confidence level has a larger multiplier. And that leads to a wider interval. So there's your explanation. So suppose you perform a hypothesis test. State the conclusion that would be made in each of the following situations. If your level of significance was alpha equals 0.05 and you had a p-value of 0.01, the question you ask yourself is p less than alpha? In this case, yes. So we would reject h naught and accept HA. Okay, here is p less than alpha. No, in this case we would fail to reject h naught. Note, this does not mean h naught is true. Okay. In a survey of 1,218 college students, 733 said that they expected difficulty finding a job after graduation. Find a 95% confidence interval for the true proportion of all college students who expect difficulty finding a job after graduation. Okay, so the first thing you have to remember is that proportion means you're working with z-star multipliers. So means you work with t-stars. Okay, so first you have to find your sample proportion. Well, your sample proportion was 733 out of 1,218, which comes out to be 0.602. Okay, and then let's just backtrack for a second and think our 95% CI is roughly going to be p hat plus or minus some multiplier times standard error of p hat. And here our multiplier will be either 2 or, to be more exact, 1.96. But the thing we need next is the standard error of p hat. Okay, standard error of p hat will be square root p hat 1 minus p hat over n. So root 0.602, 1 minus 0.602. Divided by 1,218, which comes out to be 0.014. So then our 95% confidence interval is 0.602 plus or minus 1.96 times 0.014 and 0.602 minus 1.96 times 0.014 is 0.57, we'll say 575, about 2. 0.629. So as percents, that's about 57.5% to 62.9%. So give a short sentence that interprets your interval. You say, well, with 95% confidence, between 57.5% and 62.9% of college graduates believe they will have difficulty finding a job after graduation. A 2009 survey by the Pew Research Center polled independent samples of both scientists and the general public. One of the questions asked was whether parents should be required to vaccinate their children. Of the 105 scientists in the survey, 86 responded yes, and of the 110 members of the general public, 76 answered yes. Test a hypothesis at the alpha equals 0.05 level to determine if the proportion of scientists who believe that childhood vaccination should be required is different from the proportion of the general public who should believe this. So I missed my is, but different doesn't suggest that anybody is higher. I put this question, I think, on a take-home quiz, and there I specified that the scientists had a higher proportion, but here we didn't say that. So let's let P1 equal the proportion of scientists who say yes, and P2 equal the proportion of general public who say yes. Okay, the null hypothesis is that these proportions are equal. So P1 equals P2, or P1 minus P2 is equal to 0. HA would be that P1 is not equal to P2, or P1 minus P2 is not equal to 0. So the proportion of scientists in general public who think vaccination should be required is the same. And this says that the proportion of scientists and general public who think vaccination should be required is different. Okay. Compute your test statistic. Well, this has a lot of components. First, we have to find the sample proportions. So P1 hat, that's 86 out of 105, which works out to be 0.819. P2 hat is 76 out of 110, which comes out to be 0.691. Then you have to find your null P hat value. So that's if you were to have your true proportion, what would it be? It kind of does an average of those two. And the way it does that is you figure out how many people said yes total, 86 plus 76, divided by the total number of people asked, which was 105 plus 110. And that comes out to be 0.753. So it's pretty much an average of those two, but taking into account that the sample sizes are different. Okay, now your test statistic is going to be a z-statistic, and you need the standard error. So let's just find that first, or let's just state what it is. So we'll have z equals p1 hat minus p2 hat minus this p hat minus p hat over the standard error of that null value. Okay, so that standard error of p hat minus p hat, well, that's going to equal big old square root sign 0.753 times 1 minus 0.753 over n1, which is 105, plus 0.753, 1 minus 0.753 over 110, which works out to be roughly 0.058. Now our z-statistic, our test statistic, is 0.819 minus 0.691 minus 0 divided by this 0.058, which comes out to be approximately 2.21. So next, find the p-value. Well, your p-value will be twice the probability that your z is bigger than or equal to 2.21. But z-tables don't go that way, so you've got to do twice the probability that z is less than or equal to negative 2.21, which ends up being 2 times 0.0136, or 0.0272. Finally, state your conclusion in context using alpha equals 0.05. So in this case, we reject H naught in favor of HA. And so we conclude that the proportions are different. So we can conclude that the proportion of scientists who believe that childhood vaccination should be required is different from the general public. So, several states are considering legislation that would limit the use of cell phones while driving an automobile. A researcher at the University of Utah investigated whether cell phone use impairs drivers' reaction times. 64 randomly selected students were divided evenly into a treatment group and a control group. Participants were instructed to press a brake button on a driving simulator when a red light flashed. The control, or no phone group, listened to the radio while they performed the simulated driving. The treatment or phone group carried out a conversation on the cell phone with someone in the next room. So note, this is not texting, this is talking. Each participant's mean response time in tenths of seconds were recorded, and summary statistics are given below. So first of all, consider a confidence interval for the difference in mean reaction times for phone users versus non-phone users. Why is the unpooled procedure more appropriate than the pooled procedure? Well, remember that the pooled procedure assumes equal standard deviations. And these sample standard deviations here are pretty different. So they don't appear to be close to me, so we're going to use the unpooled procedure. So find a 95% confidence interval for the difference in mean reaction times using the unpooled procedure. So just keep in mind that our confidence interval is going to be of the form x1 bar minus x2 bar plus or minus some t star multiplier times the standard error of x1 bar minus x2 bar. Okay, so first of all, let's talk about that t star. Well, looking at your t table, note that the degrees of freedom here will be 32 minus 1, or 31, because we're using the unpooled procedure. And I'm just going to use the 30 column. T is going to be about 2.04. Okay, the standard error of x1 bar minus x2 bar is equal to s1 squared over n1 plus s2 squared over n2, which is 9.8 squared over 32 plus 5.4 squared over 32, which comes out to be 1.978 approximately. Okay, so now plug in everything in. We have 5.8 minus 5.5 plus or minus our 2.04 multiplier multiplied by 1.978. So that's 0.3 plus or minus 4.04, or negative 3.74 to 4.34. Okay, so let's just write a sentence interpreting that, because even though I didn't ask for that here, I probably will ask for it there. So the mean reaction time for the phone group was between, okay, so what does that negative number mean? That negative number means x1 is lower than x2, which means the reaction time was better for the phone group. Okay, it was between 3.74 seconds better to 4.34 seconds worse, because notice that better means faster, worse means slower, than the non-phone group. So if I give you something where you have a negative, I want to make sure you know what that negative means. Does this confidence interval suggest that the mean reaction times differ? And the answer is no, as the interval covers 0. 0 is a plausible value, so we cannot conclude the mean times differ. You can't conclude that they're the same either, but you just can't rule 0 out. Okay, and our final example from this unit will be something about a hypothesis test with a mean. All right, the koala question. Koala populations have been stressed in recent years by development and drought. In the wild, koalas typically grow to weigh between 15 and 30 pounds. A random sample of 41 koalas was obtained and each was carefully weighed. The sample mean was 20.75 pounds and the sample standard deviation was 3.1 pounds. Researchers believe that the true mean weight of koalas, if it's less than 23 pounds, then the population is suffering from malnutrition. Perform a hypothesis test to determine if this is the case. Okay, so the null hypothesis is that nothing is going on, or the mean weight is 23 pounds. So mean weight is 23 pounds. Alternatively, we think that they might be suffering malnutrition, which means that the mean weight is less than 23 pounds. Okay, next find your test statistic. So because we're working with means, our test statistic is going to be a t-statistic, and it's going to be given by x bar minus your null value divided by the standard error of x bar. And remember that standard error of x bar is s over root n in this case. So here we have x bar was 20.75 minus our null value of 23 divided by, well, s over root n is 3.1 over square root of 41. If you put parentheses where I put them, you should be able to put this in your calculator. Some calculators might also default and give you parentheses here and here. So this comes out to be negative 4.65. Okay, find the p-value or p-value range. So note here that our degrees of freedom is going to be 41 minus 1, or 40. So our p-value is the probability that our t-statistic is less than or equal to negative 4.65. And looking at the degrees of freedom equals 40 row, I see that the biggest t-statistic there is 3.0. So the p-value we have is less than 0.002. So, and that's the biggest t-statistic we see. But as your t-statistics get larger, your p-values get smaller. So since our p-value is less than 0.05, because 0.05 is bigger than 0.002, we reject H0 and accept HA. So the true mean weight of koalas is less than 23 pounds. And what this means is that koalas are suffering malnutrition. And I just want to note that that's the end of this lesson, but if you look at your third midterm and use that to sort of do some more of these sample problems, you'll probably see examples of all different kinds of things, like doing hypothesis test for the difference in two means or mean of paired differences and stuff like that. Because this was a test where I had limited time, I could not do an example of everything.